Self-hosting an LLM sounds empowering until real traffic arrives. Memory gets tight, batches collide, contexts grow, and a single GPU error can interrupt inference. In this lesson, we'll look at why production serving becomes fragile and how to diagnose the failures before they spread. So far, we've seen a pattern. Demos hold up, but production exposes weak orchestration, poor monitoring, runaway token costs, latency spikes, and cascading failures. Those pressures often push teams towards self-hosting. Now we'll examine the next failure layer. GPUs running out of memory, batching under pressure, shared resource contention, and inference infrastructure that breaks under real load. With a managed LLM API, most serving complexity stays below the surface. You send requests, and the provider handles memory, batching, scaling, and isolation. Self-hosting changes that failure model. GPU memory is a hard limit, not a soft slowdown. If prompts, outputs, or concurrent requests exceed available VRAM, inference can fail outright. Since production traffic is bursty and uneven, the risk shifts from vendor latency or cost to whether your own serving stack can safely schedule work. Loading the model into VRAM is only the starting condition. It does not guarantee successful inference. At startup, the weights may fit comfortably, but real traffic adds memory that changes over time. KV cache, activation buffers, CUDA workspaces, framework overhead, and fragmentation. Long prompts, larger batches, and concurrent users can push usage over the limit, especially during prefill and decoding. Capacity planning should therefore focus on peak runtime memory with headroom, not just whether the model loads. Out-of-memory errors often happen because planning stops at model weights. Weight memory is the easy part. Parameters times bytes per parameter. So FP16 and FP32 immediately change the baseline. The harder part is the KV cache. It grows with every layer, hidden dimension, active sequence, and token kept in context. Long prompts and long generations both consume VRAM, especially under concurrency. Then add activation buffers, framework overhead, fragmentation, and traffic spikes. A safe plan reserves margin instead of running at the theoretical limit. Think of the KV cache as a memory ledger for every active conversation. As each token enters the context, the model saves key and value attention state so it can generate the next token quickly. That speed up matters, but the ledger keeps growing. One long prompt can allocate a large cache before any answer is produced. Many simultaneous requests multiply the footprint, because each sequence carries its own history. That is why a few oversized requests can push an otherwise healthy GPU into an OOM failure. Context length is a hidden multiplier in LLM serving. 10 users with short chat prompts may be easy to handle, while one user pasting a 12,000 token document can consume a surprisingly large share of KV cache memory. The same risk appears when RAG pipelines attach too many chunks, or chat apps keep every previous turn forever. Context limits are not just a user experience choice. They are an infrastructure safety boundary. Production systems need budgeting, truncation, summarization, and retrieval controls, or small traffic can still create out-of-memory failures. LM inference has two very different phases. Prefill reads the entire prompt, builds the initial attention state, and often hits the GPU with a burst of compute. That is why very long contexts can create sharp latency spikes. Decode behaves differently. It generates one token at a time, while each active request keeps its KV cache in memory until it finishes. Long outputs may not spike compute the same way, but they occupy memory for longer. Good serving systems schedule both phases carefully, so one request does not block others or trigger OOM. Batching improves efficiency, but it becomes dangerous when every request is treated as the same size. Real traffic is uneven. One request may have a short prompt, while another carries thousands of tokens. If both are forced into a fixed batch, memory use can jump suddenly. Concurrency creates the same issue. Each active sequence needs KV cache, so too many sequences can exhaust VRAM before request throughput looks high. Capacity planning should be token-based. Ask how many active tokens with their KV cache the GPU can safely hold. Static batching is simple. Wait until enough requests arrive, run a fixed group, then start over. That can work for offline jobs, where throughput matters more than individual latency. Production traffic is less tidy. Requests arrive at different times and generate different numbers of tokens, so fixed batches leave gaps. Dynamic batching adapts to timing, sequence length, and available memory. Continuous batching goes further. Finished sequences exit after each decode step, and new ones enter immediately. That keeps the GPU busy, reduces waiting, and is why VLLM uses this model. This is the pattern that makes GPU OOM feel random. Request volume rises, but the real danger is active tokens. Long prompts, long generations, and batching can expand KV cache at the same time. The crash may happen when request count is only moderately high, but token load is extreme. Once a worker times out or restarts, clients retry, adding more work to an already overloaded system. Averages will not reveal this. Watch P95 and P99 prompt length, output length, queue depth, and memory headroom. Treat every production OOM as a correlation problem, not just a GPU problem. Start with memory utilization, allocated versus reserved memory, fragmentation, and process restarts. Then connect the failure to request shape, prompt length, expected output length, active sequences, batch size, tenant, and model ID. Serving signals add more context. Queue depth, time to first token, tokens per second, timeouts, and retries often reveal pressure building before the crash. Log this metadata carefully, but never the sensitive prompt content. That is how you separate true capacity limits from application behavior. Shared GPUs are efficient, but they introduce noisy neighbor risk. A long context request can fill the KV cache, leaving less memory for every other workload. Tenants also compete for VRAM, compute, memory bandwidth, and scheduler time. A spike from one customer may not stay isolated. It can raise latency for unrelated users or push another workload into out-of-memory failure. The fix is operational. Define isolation boundaries, enforce quotas, and place workloads based on memory shape, priority, and burst behavior. Safer self-hosted inference means failing early, not crashing late. Set hard limits on input tokens, output tokens, and total active tokens, because memory pressure is usually cumulative. Put admission control in front of the GPU, so requests can be queued, throttled, rejected, or downgraded before they cause an OOM event. Isolate workloads that behave differently. Large models, VIP tenants, long context jobs, and low latency paths should not all fight for the same capacity. Finally, validate with realistic traffic distributions. Average prompts are not enough. The tails are what break production. GPU OOMs are signals, not surprises. They come from total memory demand, weights, KV cache, context length, batching, concurrency, and runtime overhead. Reliable serving means planning capacity, bounding traffic, and isolating workloads so noisy neighbors cannot take everyone down. Next, we shift from visible infrastructure failures to silent model drift, where quality regresses while the systems around it still look healthy.